Okay, now with regards to theory of chemical kinetics, actually what are we going to learn here? Okay, the theory of chemical kinetics, we are going to look into what actually happened at the chemistry level, which is at the molecular level of the reactants, okay, and products, what actually happened for the reaction to occur. And what does the postulation say? It says that the reaction rate is proportional to the number of effective collision among the reactant molecule. Collision theory, okay, it says about the postulation that molecule must collide if they want to react. Okay, remember, not all collision will produce the product. Okay, only the effective collision is going to produce the product. Okay, so basically, if you have more collision, you are going to have more effective collision, logically speaking, right? Okay, so if you have more effective collision, you are going to have a higher rate of reactions. So that's it. What is effective collision? Okay, effective collision is a collision that produce product. Okay, how do you want to achieve the effective collision? So you need to make sure the collision occur in the correct orientation. Second one is that the collision must be energetic enough. Let me just go quickly on this part. First, the reactant molecules, they must be in correct molecular orientation, in which, okay, the atoms that is going to form the bonds, they must collide. Okay, for example, you want to create carbon dioxide from carbon monoxide and also oxygen. So, the orientation of the collision must be correct. For example, here, you have CO2. So, you want to form this new bond. Okay, meaning to say the carbon must collide with the oxygen. Alright. Therefore, in this case, this is considered as the wrong orientation because the collision is between oxygen from the carbon monoxide and also oxygen from the O2. So nothing will happen. So even though they collide, no matter how hard they collide, nothing will happen. So this is ineffective collision. So example of effective collision, the carbon here, okay, they collide with the oxygen. Okay, so carbon from the carbon dioxide collide with the oxygen from the O2 gas. Okay, in that case, they will produce the CO2 as a product. So this is what we talk about the orientation. Okay, we also have another example here that you can see. All right, so maybe I will give you some kind of simulation for you to see here. Okay, look at this collision. Wow, it produces the product because that is effective collision. We can also have ineffective collision like that. Okay, there is collision but no product. So we are done to look into what is meant by correct molecular orientation. The second one is that the collision, okay, must be energetic enough, okay, only then it will produce this effective collision. Okay, so the energy of the collision must exceed the activation energy of the reaction. So what does it mean? Even though, okay, the collision is correctly oriented, okay, there will still be no product if the collision is not energetic enough, because there is some kind of energy barrier that the reactant must overcome. So what is activation energy? Okay, so this is the definition. Okay, the activation energy is the minimum energy required for a reaction to occur. Its value will varies from a reaction to reaction. Okay, every reaction will have their own specific activation energy. So now, at a given temperature, only a fraction of collision will possess enough energy to be effective and form products. Okay, but let me just share with you first about this energy profile diagram. Do you still remember that you have learned this during your high school? Energy profile diagram. Okay. Now, you have your reactant. So this is the energy of your reactant, the energy level of your reactant. Okay, and this is the energy level of the activated complex, or sometimes we call it as transition state. So the difference between the peak energy of the activated complex and the energy of the potential energy of the reactants is going to be what we call as the activation energy. So for the reaction to occur, they must overcome this hill. Okay, only then they will produce the product. Okay, let me just share with you a little bit about the graph. Okay, this is going to be important when we look into organic chemistry later. Okay, but I would like to just introduce you, okay, about transition state. The top here is what we call as the transition state. So in this case, okay, you are going to have the activation energy is going to be here. All right, and then if sometimes you don't only have one hill, you can have two hills. If you have two hills, you have intermediate. Okay, this is what we call as the intermediate. At the transition state, there is what we call as a complex. Okay, this activated complex. Activated complex, what is it? Okay, actually it is an unstable species in which, okay, they exist in neither as a reactant state nor as a product state. They are in between. They will have this kind of partial bond. So for example, this is the example of the activated complex in which this bond, okay, is about to break and this bond is about to form. Okay, so we have this activation energy. Okay, sometimes we can also include or show this through the Maxwell-Boltzmann distribution curve. Okay, so this is basically statistic part, but I think you can understand this well. Okay, so for example, this is the collision, the number of collision, of percentage of collision, or fraction of collision, whatever. Okay, this is the energy of the collision. So if some collision, they will produce this energy. Some will produce, this energy. Okay, some will produce this energy and some will produce like even a higher energy. So they will form this distribution. Okay, so the activation energy could be somewhere there. Okay, so activation energy will always be same point for every reaction. Okay, so basically, if we shade the area under the graph, this is the amount of effective collision. Okay, all right, so the energy diagram here is just to show you about the what is activation energy. Okay. So let me just mention to you a little about this. What happened when we increase the temperature? The higher the temperature, all right, so this is going to be the kinetic energy of molecules. So it's going to be the higher the effective collision, and then the higher the rate of fraction. So you can see how the temperature will affect the collision. Okay, so far I hope that you understand. So maybe I'll just include a little bit of animations or the simulation here for you to understand more about the activation energy, okay, and the effect of temperature. So now there is collision. Enjoy. With the right molecular orientation, but they are not hard enough. They did not overcome the activation energy, so there is no product. What do? I increase the temperature, so the kinetic energy is higher. So next time when they collide, they will collide with a high enough energy and boom, there is product. So now let us look into the energy diagram. Okay, so let me just share with you on how you want to draw the energy diagram. Okay, so for you to draw the energy diagram, you need to know the reaction, and also you need to know what is the enthalpy. Is it endothermic or exothermic reaction? Okay, so for example, let me just share with you for this reaction here. So you are going to have it like this and this. Okay, okay line. Alright, so now this is going to be the energy of your product. Okay, and then this is going to be the energy of your reactant. And then up here, what do we have? This is where you have the transition state, or what you call as the species is called the activated complex. Okay, so where is going to be the activation energy? So this is your activation energy. Okay, and then this is going to be the enthalpy change. Okay, so now through the theory of chemical kinetics, I have shared with you about how you want to achieve the effective collision. Okay, factors affecting reaction rate. Okay, so in general, there are going to be 5 factors that affect the reaction rate. First is the chemical nature of the reactant. Okay, this is just nature. Some reaction they are faster, some reaction are slower. Second one is the physical state of the reactants. Okay, so most reaction, okay, they are going to involve 2 or more reactants, okay, whose particles, whether it is atoms, ions, or molecule, they must collide for the reaction to occur. So because it involves collision, okay, this collision will be affected by the surface area. If you have a higher surface area, especially for solid cases, okay, you are going to have a higher rate. This is more applicable for heterogeneous reaction, okay. So the area of contact between the phase will determine the reaction rate. Basically, the higher the surface area, the higher the rate. Okay, so this is the example of the surface area. Okay, so if you just use a nail, okay, and there is a fire, okay, the reaction is not that fast. But if you have a steel wool, okay, very fine, very high surface area, so the reaction is going to be faster. Next factor is the concentration of reactants. If you remember from the rate law, if we increase the concentration of the reactant, you are going to have a higher rate. Actually, theoretically, why? Okay, this correlate back to the collision frequency. So the rate of whether is it homogeneous or is it heterogeneous reaction, they are affected by concentration. Alright, as the concentration is higher, okay, the collision frequency will be higher. So collision frequency higher, you are going to have higher effective collision, and you are going to have a faster rate of reaction. Let me just share with you example of the concentration of reactants. Okay, so now you look, I'm trying to pump in the reactants. So in total we have 4 reactants. So the collision is not much because there is low concentration. Now I keep adding the concentration to be higher, so there are more collision, more effective collision, as you can see. Okay, so I believe that you have looked into that. Now the next factor that affect the reaction rate is the reaction temperature. So for the reaction temperature, basically this is related to kinetic energy. So if you have higher temperature, basically the kinetic energy is going to be higher. So the energy of the collision is higher. Therefore, you can have more effective collision and your rate of reaction will increase. Okay? Alright. So the last one is the presence of catalyst. We are going to look into the catalyst later. So what is catalyst? Catalysts are substances that increase the rate of chemical reaction without being used up. Example of catalysts are enzymes, or you can also have metal catalyst. Okay, like this. This is the catalyst. Okay, catalysts just serve as a surface for the reaction to occur, but they did not participate in the reaction and they are not being used up. So, in total, there are 5 factors that affect the reaction rate. We are going to look into this part by part in our modules. Alright, so now let us look into how you want to answer questions in exam. Okay, first, what are the factors that can affect the rate of reaction? First is the concentration. So how you want to answer in exam, you can use 2 methods. One is that you explain based on the rate law equation. This is more common if the question asks you, what happens if we triple or we double the concentration? Okay, what will happen to the rate? And then you can explain this based on the rate law. Secondly, you can use the concept of effective collision. So basically, the higher the concentration, the higher the collision, the higher the effective collision, the higher the rate of reactions. The key is we are looking into the effective collision. Okay, so how you explain that, okay, that really depends on you. Secondly is the presence of catalyst. Okay, so what are catalysts? Catalysts are the substance that change the rate of chemical reaction without being used up. So catalysts, we actually have 2 types. Now, you can explain about the catalyst using energy diagram or using the Maxwell-Boltzmann distribution. Okay, so if you want to explain using the energy diagram, you have to draw 2 energy diagram. Okay, one has higher activation energy, that one is the uncatalyzed reaction, or you can have a catalyzed reaction with the lower activation energy, or you can explain using the Maxwell-Boltzmann distribution, okay, in which this is the activation energy of the uncatalyzed reaction, this is the energy of the catalyzed reaction. So you can see that the area under the curve is going to be more for the catalyzed reaction. Okay, next is surface area. It's usually we talk about the surface of solid or liquid reactants. Okay, liquid is something like when you do some kind of sprinkling. So the size of the droplets, okay, is going to be the size of the surface area of the reactants. Okay, why? Because if you have a smaller particles, okay, you are going to have a higher total surface area. For example, this one, this is a big particle, so the surface area, total surface area, is actually smaller, so there are smaller surface for reaction. But if you make the particle smaller, you are going to have a higher surface area. Lastly is temperature, and we are going to talk about the Arrhenius equation. So the higher the temperature, the higher the what kind of energy? Good. The answer is the kinetic energy. So the higher the effective collision, the higher the rate of reactions. So you can explain this using the Maxwell-Boltzmann distribution curve, in which you are going to have 2 curves. Okay, so these 2 curves, if the temperature is higher, the curve will be shifted more to the higher energy, so you will have a larger area under the graph. Actually, there is a way for us to calculate, okay, for us to calculate the the effect of temperature. Okay, so how do we calculate that? That is based on the Arrhenius equation. Arrhenius equation is the equation that correlates the rate constant and also temperature. So this is the equation. K equals to A. A is a constant. Exponential is exponential E there. Okay, negative activation energy divided by RT. Okay. Most of the time, it's better for you to just change it into the linear form. Ln K. Okay, this is going to be your Y. Alright. Okay, and then equals to, okay, negative EA over R. This is going to be your M. Okay, and then this is going to be your X, and this is going to be your C. So it's better to have it to remember in terms of the linear form. Why? Because we can have graphical and non-graphical method. Okay, so alright, so now this is if we have one state. Okay, at one state, this is how you calculate the rate constant, okay, under one temperature. Okay, so if you have two different condition, you are going to have different K, because K vary with temperature. Okay, rate constant. So you can have temperature 1. Okay, and then at condition number 2, you have K2 and temperature number 2. Okay, so you can equate the equation, so then you will get to this equation. There are many ways, okay, for you to express this Arrhenius equation, okay, but for me, I prefer to use it this way. Why do we need this equation? Because you can use this Arrhenius for comparison, or for you to find a K at a different temperature. This question gives you the activation energy, 587 kilojoule per mole. Okay, the half-life at 29.6, okay, is this one. Okay, and then what are the rate constant? So it's asking for K, okay, at 29.6. This is at temperature 1, okay. So the question asks what is K1 at temperature 1, and what is going to be the half-life at temperature 2. So how do we go around this? Okay, first, answer what you know first. Okay, so for a first order reaction, we know that this is the equation coming from the integrated rate law. So you can calculate the K1 at T1, which is 4.28 exponent minus 5 per second. Let us calculate for the K2 first. Okay, so K1 is given, K1 is calculated. Okay, activation energy is given. Okay, R is a constant, temperature 1 given, temperature 2 given. Remember, temperature must always be in Kelvin. So when you substitute everything, you will get to the K2 value here. Okay, so if you know the K2, you can find the half-life using this formula. Okay, so this is what you get. So this is example for us to use the non-graphical method. If we were to discuss about the graphical method, you can also use graph, okay, for you to find the activation energy and also the Arrhenius constant. This is example. You are given the temperature and you are given the K value. So in this case, the Y is going to be ln K. Okay, M is equal to negative EA over R. Okay, X is 1 over temperature and plus ln A. Okay, alright, so from this data, calculate the activation energy. What is the value of the rate constant? So now we need, because like for this question, we want you to find using the graphical method. Okay, so if you want to do graphical method, you must calculate first, which is the X value, 1 over T in Kelvin. Okay, and then you need to calculate the ln K. K is given, you just calculate the ln K. Alright, so and then you are going to plot a straight line. You are going to get the slope. Okay, you calculate the slope, for example, here. Okay, the slope is equal to M is equals to negative EA over R. So now you can solve for the activation energy. Okay, so in this case, activation energy is 160 kilojoule per mole. The second is what is the value of the rate constant at 430 Kelvin. So here, when you know what is the rate constant, okay, you know the activation energy. Okay, so we just pick any point in the data, so we can just plug into the Arrhenius equation. Okay, so we get to K1. Last but not least, let us go very quickly. I'll try to make this short, okay, about reaction mechanism. It's not really important, okay, but maybe I'll just go quickly. okay, for you to understand this, and maybe the rest you can read on your own. Reaction, most of the time, they do not occur in one single step. Okay, they can go through some kind of intermediates to get to the product. Okay, for example, okay, you form A, produce, let's say D. Okay, all right. So sometimes they do not go straight. Sometimes A form B first, B form C first, and then C only will form the D. Okay, so this is what we call as this is the overall process. Okay, and then this is the elementary process, A to B, B to C, C to D. These are the elementary process. Okay, so all the elementary process for us to get from reactant to product is what we call as the reaction mechanism. So the whole chain is the reaction mechanism. Okay, now you understand what are reaction mechanism, right? So for each of the process, let's say you go from A to B, okay, there is a there is also rate law, so we can write the rate law. Okay, from B to C, we can write the rate law. From C to D, we can write the rate law. Alright, so now let me just give you example. Okay, this one has its own rate law. This is elementary process. Elementary process has its own rate law. And then this is the overall reaction. Okay, and the overall reaction will have its own rate law. Okay, so the key value, okay, for every process, whether is it overall, is it K1, is it K2, and so on, they are going to be different. How do we know what is the overall rate constant? Okay, this is where you need to learn about the rate determining steps. Some elementary process, they are fast, some are slow. Usually, the slowest rate is the rate determining step, meaning to say, they are the steps that define the rate of reactions. Okay, whether the reaction, how long for the overall reaction to take place, it depend on the slowest reaction. So let me just go quickly a little bit. I have discussed with you about catalyst. Okay, so catalyst, what is it? It's a substance that change the rate without being used up. Okay, usually catalyst is used to speed up the reaction. Okay, how? They can alter the mechanism, like how do you go from all the elementary process? Maybe we can skip the elementary process, or we can fasten, like make it faster, the elementary process. Okay, catalysis is actually a phenomenon, okay, that occur, okay, that is caused by catalyst. Okay, you can actually have positive or negative catalyst. Most of the time, we are talking about positive catalyst. If we ask you about catalyst, you must be able to explain whether using the energy diagram, or you want to use the Maxwell-Boltzmann distribution, or you want to use this concentration versus time graph. It really depends on you. Okay. Alright, you can have two types of catalysts. One is homogeneous, meaning to say they are in the same phase as the reactants, or you can have heterogeneous, okay, in which the catalysts are in different phase with the reactants. Okay, so overall, what have you learned? You learn about the calculation part, rate of reaction, rate laws, to differential rate law, to integrated rate law, and also the half-life. So you must know about how you do calculation. Okay, these are all the important parts. Okay, and then we also talk about the activation energy, in which we discuss on the chemical kinetics. Okay, it talks about effective collision, and then in the chemical kinetics, what's important is for you to look into the Arrhenius equation. Okay, and so you can predict at this temperature what is going to be the rate constant. So if you know the rate constant, you can calculate the rate from the rate law. You should also know about the reaction mechanism and catalysis, okay, but this is not really core, okay, it's just an introduction that we give it to you. Thank you for watching. I hope that you managed to watch it all and try to attempt the exercises in the module, okay. I also give you the task on extra exercises, and as part of this blended learning, please make sure that you finish the task and submit it on YouLearn. Thank you.